Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and my guest today is Michael Weiss from the Mathematics Department at the University of Michigan. Michael, thanks so much for being here.
Thank you for having me, Sam.
And I like to say I'm from Michigan State University, and you're at the University of Michigan, so there's this bitter sports rivalry, and for people who live in Michigan, it's pretty brutal.
Yeah,
but
I guess.
What I like to say is that in education and in mathematics education, the two schools actually collaborate a lot and have a lot of cross-pollination and connections. So the rivalry, to me, doesn't feel like it goes into the math ed arena.
Yeah, not just math ed. I've never met any faculty member I used to be at Michigan State, and I've never met anybody on the faculty at either university who cared at all about the rivalry. I think that's something that sort of disappears once you get past the undergraduate level.
Yep. For me, it's fun sometimes to just crack a smile with somebody else from it, but it's always in this kind of friendly way because there's no actual anger beneath it. But I'm happy to have somebody here from the University of Michigan.
Well, thank you.
We're going to be talking about your new book called Secondary Mathematics for Mathematicians and Educators, A View from Above, and that's from Routledge. And so I'm kind of excited to talk about this book, Michael, because I teach a course that's kind of like secondary topics, but from an advanced perspective, we call it.
Yeah,
and
you're the target audience for this book.
Yeah, we have kind of a mixture of things that we draw on for that course, but as I think other university instructors probably know, it's wonderful when there's a book that kind of brings it together into one place, and it can be sort of a central resource. So I'm happy to dig into that book soon. But first, I do want to just back up a second and get you on the map in terms of where you did your graduate school studies and what your dissertation was on, just briefly.
Sure. So I did my doctoral work at the University of Michigan. I actually went through two different doctoral programs at Michigan, separated by almost a decade. Briefly, I started out in a pure math PhD program in the mid to late 90s, and I worked on that for about 5 years. And then I left that program as an ABD and went and taught high school for the next 5 years. And then in 2005, I knew somebody who knew Deborah Ball, and that person suggested I should talk to her about possibly returning to graduate school with a focus on math education. And that meeting turned out to be incredibly fruitful. I ended up meeting not only Deborah, but also Hyman Bass and Patricio Herbst, all in that one afternoon. It was very fateful for me, and started back into grad school in math education. And then I finished my doctoral program with a joint degree issued by both the math department and the School of Education at Michigan.
Okay. And Deborah Ball, another one that kind of cross-pollinates from Michigan State and the University of Michigan.
That's right.
What was just briefly the topic of your dissertation study?
So my dissertation was on the role of the secondary geometry course in cultivating a mathematical sensibility among students. The first part of the work was really defining and articulating what I meant by a mathematical sensibility. So that was partly theoretical work and partly empirical work, based on a literary analysis of memoirs and biographies by and about mathematicians, trying to understand what is it that mathematicians care about that is distinctive to the profession. Then for the second part of the dissertation, I turned to two different empirical sources. One of them was a collection of focus groups that had been run by Patricio Herbst as part of his research study, Thought Experiments in Mathematics Teaching. And we would convene teachers together around representations of imaginary classroom scenarios represented in the form of animated cartoons and comic strips. Some of your listeners may be familiar with the Lesson Sketch project, which came out of the Thought Experiments program. And we would ask teachers, if you were in this situation, what would you do? Or would you put yourself in this situation? What would you do instead of this? What do you think of a teacher who teaches this way or students who behave this way? And that would be the launching pad for really fruitful and interesting conversations that would reveal a lot about what teachers cared about and what they wanted their students to care about. And then the last piece of the study was an analysis of assessments that I had written when I was myself in that 5-year period of a high school teacher. Because I felt, I didn't really have an intellectual frame at the time for describing this, but I felt like because I hadn't come from an ed school background, because I had come from a background in pure mathematics, there was something about my teaching that was different. And I didn't think it was necessarily that I was a better teacher. In fact, I'm sure in many ways I was not a better teacher. But that there were certain things that I cared about that were atypical. And I wanted to try to understand what were those things, and do those things show up at all in the things that I held students accountable for, which would be the assessments that I gave them. So it drew on a variety of different sources to try to understand, is there a way that a high school class can hold students accountable and can cultivate an opportunity to develop the kind of sensibility that's characteristic of what mathematicians do in their practice.
So now I'm glad I asked that background question, because I can hear that actually a lot of this is what's positioned you to write this book.
Yeah, absolutely.
And the book, Secondary Mathematics for Mathematicians and Educators. So again, kind of at that intersection of the mathematician's point of view, but also bringing it to an educator audience. So I first want to just now ask you, when did you get the idea to write this book, and what was it that kind of spurred you on to take on this project?
So before there was a book, there was a class. When I had my first job after grad school, I was teaching at Oakland University, which, for your listeners who don't know it, that's in Oakland County, Michigan.
Michigan, yeah, that's where my wife graduated from. Yeah.
Oh, really? Okay.
Yeah, my wife was the number one music educator student. She gave the speech at the graduation at Oakland University that year.
Oh, we're going to have to talk after the interview about music education, because my son is graduating with music education right now from Wayne State.
Oh, wow.
When I had started teaching at Oakland, I was my position had that same kind of intersectional role. I was part of the College of Education, but about half of my teaching load was in the Department of Mathematics, and I was the liaison between those two programs. And about half of my teaching responsibility was Math for Teachers courses. And there was an interesting, what seemed to me to be an interesting hole in the course catalog. There were courses in mathematics for elementary school teachers, or pre-service elementary school teachers. And there were methods courses for both pre-service elementary and secondary school teachers. But there were no courses that were specifically for pre-service secondary mathematics teachers. At the time, at least, that cohort of students took the standard math major courses. They had to take linear algebra, they had to take abstract algebra, the same set of course requirements that any math major would have to take, but there was nothing specifically about education or teaching that was in mathematics. And when I asked why, the response I got, which I think was very revealing, was that, well, these were all undergraduate math majors. They all knew secondary mathematics very well. There was no reason to have them take courses in secondary mathematics. I felt that that was revealing, first of all, because I think it communicated something about how they thought about their elementary school teachers. The elementary school teachers don't know elementary school mathematics. That was the conventional wisdom. And so they need remedial coursework in elementary school mathematics, which is not, in my mind, what the role of a course in mathematics for elementary school teachers needs to be. But that's how the math department saw it. And they also felt, sort of the corollary of that, was that if you don't need a remedial course in secondary mathematics, there's nothing else to teach. And I felt very strongly that there was, in fact, something that a pre-service secondary mathematics teacher could learn about the mathematics they're going to teach that they would not already know, that would give them an advanced perspective on the content of the secondary curriculum. I was not thinking explicitly in terms of the model of mathematical knowledge for teaching at the time, but I think maybe subconsciously I was thinking about that idea, that there is mathematical knowledge that teachers bring to bear on the teaching of the subject that goes beyond the content they're actually delivering or teaching to the students. And that includes things like horizon content knowledge and knowledge of the curriculum, all of those things that get wrapped up in the MKT model. And so I wanted to develop a course that focused on those things. So I taught that course. I taught a course like that at Oakland 2 years running. And then when I changed institutions and went to Michigan State, I had the opportunity to teach it again, each time for a different group of students. But by the time I had done it 4 times, I felt like this is a book. This is ready to become a book. And so then I took a few years to take all of my notes from the course and turn them into a book. But that's really where the book came from.
And that is, just to be clear, this is a one-semester course?
It was a one-semester course, that's right.
Yeah.
The first time I taught it, the students who took it were actually, this is a little bit ironic because I just gave you the reason why PSTs need to take the course. And when I actually ran the course, I didn't have any PSTs take it. It was actually for institutional reasons. The only way to fit it into the schedule was as a master's level course in mathematics. And it was taken exclusively by mathematics graduate students who had an interest in, so many of them were former classroom teachers who had an interest in moving into the community college sphere. So they were getting a master's degree, or I think in one case they were working on a PhD in mathematics, but it was with the intention of going on and being a community college faculty member. And so they were also interested in an advanced viewpoint on the secondary curriculum, and it made sense to teach a graduate level mathematics course on the secondary curriculum to them. Then at Michigan State, the cohort that took the course was exclusively math ed doctoral students who had a completely different set of reasons for wanting to take this class. They also needed, for institutional reasons, a graduate mathematics course because it's part of the doctoral requirements. They had to take some cognates in the mathematics department. Most of them in prior years would take, a class in graph theory or a course in differential geometry or, some sort of generic mathematics course that was at the 400 or 500 level that didn't really have a lot to do with their intended careers as mathematics educators or scholars or teacher educators. And so this, again, seemed like a course that would make sense for them, something that would fulfill the institutional requirement for them to take an advanced level mathematics course that was really a math class, but also was relevant for somebody who wants to work in the field of secondary math education.
Mm-hmm. Yeah, and I'll add, too, here at Missouri, we have practicing teachers who are getting their master's degree, and so they might have had the pure math courses in their background, but they would still rather take a deeper dive into the secondary mathematics kinds of topics. As we take that dive, I want to ask you about your thought process for structuring the book, because I know when you take a course but you turn it into a book, I'm imagining there were probably some interesting decisions about how you wanted to lay out not only the chapters, but also you have kind of a pattern of the certain elements that are in the chapters and in the sections.
Yeah, so partly that came from thinking about who the audience was. I wanted a book that would be useful for doctoral students in math education, graduate students in mathematics who were interested in the secondary curriculum, and in-service teachers who were returning for a master's degree in mathematics, or to a lesser extent, pre-service teachers at the end of their studies. And those different audiences need different things. The core of each chapter is a mathematical analysis of something. But within each chapter, I wanted to begin with a launch that was focused on the history of the curriculum, which is something that I think is underappreciated. I don't think we pay nearly enough attention as practitioners and as people who teach practitioners to understanding how the curriculum has changed over the last 50 years. I think there's a lot that can be learned from understanding how, things that used to be in textbooks and are no longer in textbooks, or things that are still in textbooks but have changed the way they're presented.
Or why were they put in there? A little bit of the reasoning, but from
why did they come in and why did they go out? And why do some things disappear and other things persist? So, chapter 1 is really, the beginning of chapter 1 is really about the new math. Mm-hmm. And I ask the question, of all the innovations that were introduced during the new math area, nearly all of them have disappeared. But there are a couple of things that persist, that stick around. One of them is inequalities. Inequalities are still here, right? Many people don't know that before the 1950s, that was not part of the curriculum. But you can pick up math textbooks from the 1930s, 1940s. Say an algebra or an Algebra 2 student would not be expected to solve inequalities. That simply was just not part of the curriculum. Even the symbols for less than and greater than rarely appeared in secondary textbooks. That was introduced by the new math, along with things like mathematics and other number bases, and a vocabulary for distinguishing between numbers and numerals, and the set theory language and notation. Almost all of that fell away, but inequalities survived as sort of vestigial organs left over from a transplant that somehow didn't take full root. Another thing that survived is the language and visual representation of hierarchies of sets of numbers. So you look at any algebra textbook and you open up to chapter 1 and you're going to find a Venn diagram that shows the whole numbers sitting inside of the integers, sitting inside of the rational numbers, sitting inside of the real numbers. And if you go to an Algebra 2 textbook, you're going to find about 2/3 of the way through the book the same diagram repeated, but this time showing the imaginary and the complex numbers. That way of talking about types of numbers as sets that are enclosed within one another in a hierarchical relationship, that was not part of the language of mathematical instruction. Certainly mathematicians talked that way. But it was not part of the secondary curriculum until the new math. And it survives, again, as a sort of a vestigial organ because we include these diagrams. And then usually there's a little bit of work around identifying, what kind of number is this, right? What kind of number is the square root of 2? What kind of number is 3/2? Which of the following numbers are not integers? But you don't really do much with it. You get out of that first chapter and it gets forgotten about. So I was interested in trying to understand, why did these things stick around, despite the fact that they don't really get used all that much, and especially in the context of so many other things falling away. And an answer that I propose, this is really an unanswerable question, but one thing that I think I've come to believe is that the reason those stick around and the reason those took such deep root in the curriculum is because there was a time in the mid to late 60s when the goal of high school Algebra 2 was to construct and define the set of real numbers as the unique, complete ordered field. That was considered a mainstream goal for high school students. Now, anybody who teaches high school nowadays thinks that's crazy. That's bonkers. The idea that you're going to devote, 1 or 2 months out of the high school year to, first of all, explaining what a field is, then explaining what an ordered field is, and then defining a complete ordered field and focusing on things like the least upper bound property, the completeness property of the real numbers. And then even saying things like, up to isomorphism, there is a unique, complete ordered field. Like, the idea that that would be something appropriate to do in the high school setting seems outrageous today. But I think that was clearly the goal in the late 60s. And if you look at old textbooks, you can see that. I mean, I find that in the tables of contents. In order to do that, you need a language of sets. You need to have a hierarchy of sets that are included inside of other sets. And crucially, you need inequalities. So those things were necessary for that educational goal in a way that some of the other innovations of the new math were not. Mm-hmm. And even though the goal is no longer included in the curriculum, the tools that once facilitated that goal have stuck behind, like fossilized footprints from a dinosaur that's gone extinct. Like you can still see the tracks, even though the creature's no longer living with us. So anyway, I thought that perspective is something that is interesting as hell and also useful.
Yeah. And to me, looking at it, you do start the chapters with that little bit of kind of curricular history context, right, which I think is interesting. But it's also in a kind of a bite-sized form, where it doesn't become a history textbook. It's kind of like, let me just give you a little bit of context before we dig into some of this math. I also noticed that and I'm sure you had some thoughts behind this, like, at the end of the chapters, you also kind of connect to some mathematics education literature and you have like additional readings, but you also sort of put some thoughts around those additional readings. So it's not just like a list. And then you even have like projects that you might do with the students, or like, what are some thoughts for that part of the structure that you built in?
Sure. So that came out of my third and fourth time teaching the course when I was working with math ed doctoral students. And I felt, because of who they were and what their career goals were, it was really not enough to just give them math problem sets. I mean, we did math problem sets, but these were people who were preparing for careers in math education. They wanted to be scholars in the field. They wanted to be teacher educators. And so I thought part of my purpose in running the course is to familiarize them with some of the literature in the math education field. The math education, as you know from running this podcast, certainly is an extremely diverse field. There's a lot of different ways that people approach math ed. Some people are very focused on things like discourse and student affect and dispositional things. And some math ed research is much more focused on the intersection between content and practice. And I thought this is a good opportunity to focus on that latter slice of the research. There are some wonderful papers, some of which are landmarks in the field, that really focus very closely on how the mathematics interfaces with the teaching practice. I'm thinking, for example, of Salyusiskin's papers on the role of variables in high school algebra. Or there's a wonderful paper by Eli about a student's non-standard conceptions of the real numbers that involves non-standard analysis as sort of an instinctive student construct. To really understand those papers, I think you have to understand the mathematics at a deep level. And it turns out that what I was writing about in the math content part of the book, which again is most of the book, is just math, had deep hooks in that research literature. And so I wanted to not, as you say, not just give students some more reading to do, but also guide a little bit how they should think about those readings and how it connected with what I had written, and give them some projects that they could work on so that the book would be more usable for people teaching in a variety of different contexts.
Mm-hmm. I want to ask you about a couple of your favorite spots in the book, but I also wanted to lay out for the listeners the chapters that you do have. So you start with the number and number systems. You go to polynomials, then you go to equations, and then there's a geometry, graphs, and symmetry chapter, and then you finish up with exponents and logarithms, and then complex numbers at the end. So with that lay of the land, maybe if you want to just share one or two kind of spots that you're especially proud of or that you really enjoyed writing.
Sure. So I think the things that I found the most pleasure in were the places where I was learning something new as I was teaching the course or as I was writing the book. And there are two that come immediately to mind. So in the chapter on polynomials, my approach to that chapter was to ask the question, what happens if you take the theory of polynomials as it's taught in high school, and you just change the rules a little bit and you let yourself work with polynomials whose coefficients come from other sets? So for example, if you write down an equation like x squared plus 1, or a polynomial like x squared plus 1, you can interpret that as a polynomial with real coefficients, but you can also interpret the coefficients as belonging to another set, like let's say the integers mod 12 or the integers mod 5. One of those is a field, the other one is not. How does the theory of solving polynomial equations, the theory of factoring polynomials, change when you change the interpretation of the coefficient ring? That's a pretty abstract mathematical question. And one of the things that I did not know until I started working on the material, I think it wasn't really until the second time I taught the course, but I sort of realized this as I went, is that, so this is a little bit complicated to explain verbally, but I'll do my best. If you are working with polynomials whose coefficients are from the integers modulo some prime p, then any function you can write down from that set of integers mod p to itself, any table of values you make up, can be represented by some polynomial. Every function is given by a polynomial. There really are no transcendental functions when you're working over a prime number, a prime characteristic. And in fact, the number of possible functions is p to the p power, and the number of distinct polynomial functions is also p to the p power, and there's a one-to-one correspondence between the two of them. But if you work over the integers mod n, where n is a composite number, things are extremely different. It turns out that most functions can't be represented by polynomials. In fact, if you write down, say you're working over the integers mod 36, if you write down a random table of values where, the x table goes from 0 to 35, and in the y table, you can put down any numbers you want between 0 and 35. And you ask the question, what's the probability that there's a polynomial that describes this particular function? The likelihood that the answer is yes is smaller than the probability of picking a single atom out of the entire universe at random. That is how scarce, that is how rare the polynomial functions are among the functions over the integers mod 36. But if you change to the integers mod 37, the probability changes to 100%. 100% immediately. I thought that was amazing. I still think that's amazing, that so much hinges on that one small change of rules. And developing the theory that sort of explains all of this turns out to have a lot in common with the high school curriculum in ways that, again, I think, your listeners may be skeptical that it's relevant for a high school teacher, but it turns out it goes back to the factor theorem and the remainder theorem, which are mainstays of Algebra 2, right? Every Algebra 2 textbook that I've ever seen covers that content. And if you want to know why are those theorems true, it depends on what kind of ring you're working over. And so the book is about making those kinds of connections.
Right. And so you mentioned like a listener might be skeptical, but again, I just was having taught a course like this, it's always important to kind of clarify that the stuff in the book is not meant to be taken and then done directly with 13-year-olds or 14-year-olds.
Oh God, no.
These are the things that it can be fun and engaging for math educators, for teachers to engage in, and it can give them some insights and some depth of understanding that then helps them see the secondary curriculum in a whole new way. Because like, wow, I really see, it's like X-ray vision. I can see that mathematics and what's behind it, and so it gives you this new lens onto it.
That's right. That's what the MKT model calls horizon content knowledge, the ability to see the mathematics that is ahead of the mathematics you're currently working on. And I'll also say in that connection, my very first semester teaching methods at Oakland, so I was teaching pre-service secondary methods class, and most of my students, actually all of my students at the time, were also taking their undergraduate math courses. They were taking abstract algebra. And they would come in literally every day and complain about this stupid abstract algebra course they had to take. It was completely irrelevant for them. They didn't understand why they needed to learn this. It had nothing to do with teaching high school. And there came a day when we were talking about exponential functions in the methods class, and how would you teach exponential functions? What are the big ideas that you want your students to come away with? How would you assess those big ideas? One of my students in the methods class proposed a really big idea is that there's an analogy between linear functions and exponential functions. And she articulated very well that, in a linear function in slope-intercept form, you have the y-intercept b tells you the starting value. And an exponential function in standard form, you have y equals a times b to the x power. The a gives you the y-intercept, which is the starting value. And also, the b, the base of the exponential function, plays the role of the slope m in the linear function. And we talked a lot about that, and I think most secondary teachers and secondary teacher educators would agree that that's a really insightful connection, and that's exactly the kind of thing you want your high school students to understand when you're teaching this course. And I said, being a sort of naive first semester university faculty member, I said, you're calling this an analogy, but there is a mathematical name for it. You're describing an isomorphism between two groups. I mean, there's the group of real numbers, and there's the group of positive real numbers. And the function that takes x and turns it into e to the x, or b to the x for some base b, is an isomorphism between those two groups. And the reverse function, the logarithm function, is the reverse isomorphism. It's the inverse function. And that isomorphism translates linear functions into exponential functions and vice versa. That's what exponential and logarithms are. They're isomorphisms between two groups. And there was this moment where there was just a pause, and then one of the other students said, I think I just learned more abstract algebra in the last 5 minutes than I did in an entire semester of this course, right? The point is, the abstract mathematics is relevant. It is connected to the high school course, to the high school curriculum. But those connections are not automatically made visible. They don't just present themselves to the student. You have to make the connections visible for them, and that's really what I was trying to do in this book.
Yeah, and I've always found it more beneficial to notice that the students are making meaning. Like, so they're making a meaning of like, oh, there's kind of the starting point, there's kind of the growth, and then to provide language to that meaning.
That's exactly right.
I've always found that being more effective than trying to start with the language and be like, let's learn about isomorphisms. I'm going to tell you about their features and stuff. When they've noticed something that kind of makes sense to them, and then you say, here's language that actually describes what you're seeing already, like that seems to me like when it clicks usually better.
I think that's exactly right. I think we see that even at the elementary level, right? Even elementary school teachers notice that the rules for combining even and odd numbers are kinda just like the rules for combining positive and negative numbers. They know that there's some kind of analogy there. They don't know how to describe that analogy. And you don't necessarily have to do an entire semester worth of group theory with them and then say, this explains or this provides a language for talking about what you've noticed. It's helpful for people to have a language for describing precisely the things that they already are recognizing.
Mm-hmm. Really quickly, I think you mentioned there was a second favorite one that you enjoyed learning about.
Yeah, so I'll try to be brief about this one. This involved complex numbers. The last chapter of the book, which in many ways is self-contained. You could skip every part of the book and just go straight to chapter 6 if you want. It's kind of a set piece. Is about what are complex numbers and why do we define complex numbers the way we do. There's a lot of different ways to approach the study of complex numbers. I think most, historically at least, the two approaches are to just regard them as sort of fictitious objects that you manipulate and you don't worry too much about their ontological status. So that's certainly how mathematicians thought about complex numbers until the 18th century, maybe 19th century, really. Yeah, because Hamilton was 19th century. And then the second approach is to say, well, no, what we're doing is we're defining a multiplication law on the set of two-dimensional vectors. And the way that multiplication law works produces a structure that looks like complex numbers. So when I have tried to teach complex numbers that way, the immediate pushback I get from students is, well, why would you define multiplication that way? If you're trying to define a multiplication law for two ordered pairs, that's not intuitive to define them this particular way. So I took that as an invitation to say, well, let's see what our other options are. Maybe there's other ways we could define multiplication in two dimensions. And of course, there's infinitely many different ways you could define multiplication in two dimensions. But it turns out that no matter how you define multiplication in two dimensions, at the end of the day, there's only three different kinds of structures that you can get, and only one of them is a field. And that's usually thought of as a pretty high-level abstract result. I mean, I think here at Michigan, we teach that to our first-year graduate students in mathematics. But honestly, the proof requires nothing more than some very basic undergraduate linear algebra. And so for my target audience, which would be, teachers at the end of their undergraduate career or people who are coming back for a master's program, if you know what a determinant of a 2x2 matrix is, you can understand that proof. And I think it's a lovely little result that is very unexpected. And again, it sort of explains why things are taught and structured the way they are, that there is a certain amount of inevitability to certain mathematical structures. And although we have lots of freedom in deciding how we want to do things, at a certain point, the mathematics pushes back at us and makes us go down specific roads, whether we want to or not.
I'm speaking with Michael Weiss from the University of Michigan about his new book, Secondary Mathematics for Mathematicians and Educators. The last question I wanted to ask you about the book is just if you were talking to a student or an instructor who had just used your book for a course. So you've now kind of taken your experience and your insights, you've passed it on, they've tried it out for a semester, and you chatted with them at the end of the semester. What would you hope that they would say to you, or what would you hope that they would kind of reflect upon at the end of their experience?
So I'm going to answer that question in two parts. It depends first who the instructor or the student is. If the instructor is a mathematician, well, look, I called the book Secondary Mathematics for Mathematicians and Educators partly because I wanted to write a book that a mathematician would appreciate. I wanted to push back against the sort of naive assumption that anybody who's mathematically sophisticated already knows everything there is to know about the secondary curriculum. And what I would like to hear from a mathematician is that they now think the secondary curriculum is a lot more interesting than they previously did, and that they actually learned something, even some math that they did not know from this book. And I really do hope that that is what they would have, the experience they would have. From a student in the course, I think what I'd most like to hear is that they fell back in love with math after taking this course. One drum that I have been banging for the last 20 years is that we spend an awful lot of time convincing students that math is useful and important. And we don't spend nearly enough time convincing students that math is interesting. And those two things don't have to be in conflict with one another. They're really orthogonal, you know? Something can be useful, and something can be interesting, and something can be both. And those are just different ways of appreciating what math is for. And I would love to have my future readers of this book come back to me and say, I learned a lot. I think this book will be really useful to me as a teacher, but also, wow, it was interesting. I just never knew this stuff, and I want to know more about it. That's the kind of response I'm really hoping for.
Yeah, I was recently reviewing Andrew Hacker's book about the math myth, and one of the things that he says in there is, you know, mathematics has more opportunities than most any subject to like present itself to people, and it has a pretty terrible track record of actually showing itself to be interesting and like a fun and engaging kind of subject.
Yeah, he's right about that. I mean, I think Hacker's wrong about a lot of things, but I think he's right that we emphasize the utility of mathematics to our peril, because everybody knows that a lot of what we teach at the high school level is not useful for most people. That doesn't mean we shouldn't teach it. There are other reasons to teach it. You know, I think most of us in academia still believe that the value of education should not be limited to what you can do with it at a pragmatic level. There's reasons why we teach people literature. There's reasons why we have courses in history and philosophy. It's not only about utilitarianism. Mm-hmm. And I think mathematics should be part of that. It's one of the liberal arts. It should be understood as a great accomplishment of the human mind. And honestly, if it's taught correctly and if it's approached from the right point of view, it's fascinating. We should lean into that. It's one of the best things we have.
Yeah. Now, what if you weren't in mathematics and mathematics education? What would you maybe do as a completely different alternative?
Well, this is not really a hypothetical for me, because I took a number of different twists and turns in my career path, and I almost became several different things. At one point when I was an undergraduate, I knew for sure that I wanted to teach at the university level, but I didn't know what I wanted to teach. And I, for a good 6 months, was really seriously considering going to grad school in English literature and specializing in the 18th century English novel. I just love the 18th century English novel. I mean, I think I was the only person in my English lit course that just really loved Joseph Andrews and Tristram Shandy and Shyamala and Pamela and some of those wonderful early novels from the dawn of the genre. So I could see myself doing that. I could definitely see myself doing that. At one point, I considered going to rabbinical school. I gave that a lot of consideration for a while, and becoming a full-time Jewish educator. I thought about being a science journalist. You know, sometimes I look at books by people like Brian Greene and other really good writers of science for a popular audience, and I think, oh man, I could have done that. I could do that. I could still do that. Maybe I should do that. So those are all different directions that I could see myself doing.
Well, I do appreciate that you took the time and effort for this book, and I'm looking forward to the next time that we have the course here, which I think will be in the summer, actually. So thank you so much for sharing your insights on the book and your work that went into it.
Well, thank you so much for having me. It's a great pleasure to talk about it.